This presentation is something to do with the design of microwave integrated circuits. When you say design, there are only three things, parameters one has to decide. One is the length, the other one is the width, third one is height. Out of these three, one is manufacturer's concern. Um, Unless otherwise specified in the whole world, it is 1/16th of an inch, or you can call it as a 1.6 mm. So one need not bother about the height of the substrate. So what he has to design is what is the length and the width of the components. Components, I mean, what one person print or use in the satellite. You know, regarding India, they were successful in the Mars mission. At the first attempt, it reached. Likewise, Chandrayaan-2, then human space mission is yet to get launched. So in all this, wherever there's miniaturization is the mantra, microwave integrated circuit will come to rescue. And the backbone of the microwave integrated circuit is the planar transmission lines. So I have seen many of the researchers, students keep mugging up or keep referring previous journal papers. What I feel is it is not as people think. Microwaves or electromagnetic theory, antenna, they are not at all difficult. If you understand, it will be a child play only. And there are only 10 equations, four Maxwell's equations, four boundary conditions, and two Helmholtz equation, or otherwise called wave equation. So now anything you say, we should find out its
Ex
equivalent. Yes, yes,
Excuse
please.
me. Yes,
Ah,
sir. Can you please on your video and just full screen the presentation?
okay, can you see
Yeah.
me?
Yes, and do the full
Uh,
screen.
Full screen I will go. Just to tell me whether it is coming out
Yeah,
properly.
video. Yes, yes.
Is it okay?
Yeah, that's
Uh,
perfect.
okay.
Yeah.
Okay. This is the one. Um, See, everything is in lambda. See, waveguides are there. Certain cases, waveguide also will not be used. You should go for integrated circuits. And that at microwaves are called microwave integrated circuits. And the backbone of the microwave integrated circuits are well known: strip technology, microstrip, slot line, coplanar waveguide, coplanar strip, fin line, like that. So in any case, the only mantra is miniaturization. So you can design any component. Any component means either in Singapore or India or anywhere else. There are not more than 10 components in the whole world. Maybe the size will be different, the material will be different, but the theory of designing is very same everywhere in the world. So that way, it is not only in defense, not only in space applications, it plays a very big role in the health technology also. Now the whole world is very much concerned about the COVID. Even the COVID can be detected through our microwave integrated circuit. You know very well, CT scan, MRI, and all biomedical instruments, they scan, they do the diagnosis and therapeutics. But which technology will save CT, MRI, ultrasound, all those medical instruments? Yes, it is the same microwave integrated circuit technology, or millimeter waves, or frequency selective surface, metamaterials. These technology will have a EMI shielding that will save CT scan, MRI, things like that. So what I want to tell is these electromagnetic technology not only is used for defense, space technology, it plays a very big role in the health technology. So one need not bother about the designing of the components, uh, length and the width. As far as the width is concerned, it all depends upon the characteristic impedance. you can make use of Wheeler's curve and other 2 nomograms and then get it. The next part, 50% is the length. If you know the sanctity of the length, that's why I say splendors of lambda or magical lambda. So if you know it, 0 to lambda, there are infinite lambdas. Each lambda is of much usage. Or the converse, if you know the application, you can know what is lambda g. See, lambda g, when I say, it takes care of all the materials because it is equal to lambda naught by root of epsilon effective. If it is a inhomogeneous, it is epsilon effective. If it is a homogeneous, it is epsilon naught. So the first slide is the cake. What you see, that Smith chart, it is not just for playing sake. Somebody, one postgraduate student, he has done using JPG format. And this was formed by P.S. Smith in 1938. Whatever one wants to tell about the transmission line theory, the whole thing is engraved here. Whether it is in Singapore or America or Australia or India, there are only two elements. One is inductor, other is capacitor. That can be connected in series or it can be connected in parallel. So if it is so, that can be accompanied by this circular one. The upper one is inductor, the lower one is capacitor. The same thing if you put it in the immittance chart, impedance and admittance are all 90 degrees apart. You shift every point by lambda g by 4. Then you will get parallel susceptive capacitance, susceptive inductance. So that way, there is nothing that you cannot solve from this Smith chart. What a 40 lakhs instrument network analyzer can do, this can do. And this is called the significance of lambda. In another, by the time I complete my small talk, you will come to the conclusion. If you know the lambda, you can design any of the components for any of the transmission lines. What is getting changed is only the epsilon effective. For a layman's point of view, I can say in the microwave oven, normally people put chicken, mutton like that. So that material, we call it as a epsilon naught. Each part of a chicken has got different epsilon naught. Even if you take a man and woman, it has got, a brain has got epsilon r is equal to 50, air epsilon r is equal to 1. Women also has got different epsilon naught. That is one of the reasons why people say microwaves are friendly with women. The take-home story is, if a man cooks with a microwave oven, something bad effect will happen. But if women cooks, nothing will happen. So this is a small kind of note to know about the epsilon naught. So that is how one can distinguish between effective epsilon and relative epsilon, epsilon naught and epsilon effective. So the lambda, most of the researchers know three lambdas, lambda g by 4, lambda g by 2, lambda g by 8. It is not only those three, there are many lambdas I will just show. This is another Smith chart in a different way. People say Rangoli or some column like that. So this is also an art of a Smith chart. These are all, maybe it may be looking colorful, but it's all in terms of different calculated lambdas. Each will signify certain applications of a microwave component. Everyone is aware of 10 commandments promulgated by Moses. The same thing, we have got 10 commandments for MIC. First one is, thou shalt be aware that micros are very high frequencies. We never talk anything less than gigahertz. That's why centimeter, millimeter. Now we talk about terahertz and all, 5G, 6G and all. So that way, the last commandment is, but for microwaves, present day technology would not have come to this enormous development. So this, okay. Okay, like that, I can say the reference book. there's a book by Levergeta. Once I show the 10 commandments, I should be able to tell so many Bibles name. There are Bibles for each of the topic. Bible means no other book can match. So the 10 commandments, it is from Levergeta. The first page is 10 commandments. That is the principle of microwave, antenna theory, anything you tell about EMT. Then next comes, these are the things. There is nothing other than whatever you are seeing in this. I think I will go to slideshow. Uh, okay. Okay, sorry. Okay. I think I will go in this mode itself. Otherwise, some see there are these are the materials. One is meta material, SIW technology, photonic band gap PPG, EPG, then FSS. FSS is the hottest field today. Then antennas, DRA, transmission lines, waveguide, microwave components. So meta material, physical meaning is beyond nature. It was initially it was a patent of Marconi, but that was slightly developed by some information was given by J.C. Bose. Then further it was developed. More informations were given by Victor Veseligo and Penry. Metamaterial is in no way different from the transmission lines. One should be thorough with the transmission lines, replace every epsilon and mu by less than zero, negative epsilon, negative mu. See, the microwaves, it will travel only straight lines. If you want to bend it, like laparoscopic surgery, gastroentomologist, you need a laparoscopic pipe to bend it. So microwaves cannot do it. But if you can impregnate with metamaterial, it will bend it. So how to design that? That is also in terms of lambda. Next, planar transmission lines are very good as far as the miniaturization is concerned, but it cannot withstand very high power. But waveguide can withstand very high power. It cannot hold good for miniaturization. So if there's a bridge between these two, it will be nice. That is substrate integrated waveguide. If we want to design SIW, there are only four principles. What should be the distance between the consecutive holes? What should be the difference between the consecutive parallel lines? All are only in terms of the lambda. Likewise, photonic band gap. Everything in terms of lambda. If it is the unit cell size is far, far less than lambda, it is beta material. If it is almost equal, it is the photonic band gap. So in terms of lambda, you can distinguish beta material, photonic band gap, and also electronic band gap. Then frequency selective surface. Maybe the name is different, but it is nothing other than spatial filters. If you see the structure, one particular structure, very popular one, the length is 1 by 3 lambda. See, now I have gone to some other lambda. Lambda g by 4, lambda g by 2, lambda g by 8. Now lambda g by 3. So that you can see. So there is no need to know where is the formula and all. If you know lambda g, first using the frequency, find out lambda naught, divide by root of epsilon effective, then you get lambda g. Then in some cases it is lambda g by 10, some cases it is lambda g by 20, some cases it is lambda g by 3. You can easily remember how much is the lambda g. So in that case, it is you can easily design for any material. Many material, what I mean is archiduride, alumina, Teflon, sapphire. Take any material, take any kind of planar transmission lines. This is sufficient. Likewise, antenna. Antenna you call resonator. Each width and the length is lambda by 2, lambda g by 2. Only thing is because of the fringing capacitance, you remove some correction factor left side and right side. So in any case, it is only lambda g by 2. Now subtract some portion in the left side, some portion in the left side. And as an engineer, you cannot say some and all. There's a very accurate values are there. That also you can derive only in terms of the lambda. The next one is you take a waveguide, fill it up with the dielectric, then it has got a peculiar property. We have got a very good Bible for that, written by Mongia. So in a short time, I will be able to say one or two Bible's name. That is a ocean. You can go through that. Likewise, the transmission lines. See, transmission lines, the best book is Johnson. Like that, there are some good Bibles, each of the thing. Likewise, waveguides. Best book is Antigo, then micro components. So that way you can refer, and there is no need of Maxwell's equations. If you remember this equation, find out the voltage at any point, current at any point of a transmission line, divide, then this is what you get. And if it's a lossless transmission line, you get this. This is sufficient to design any components, whether it is in the space satellite or DRDO defense applications or in medical applications. This is sufficient. Maxwell's equation is not needed. In fact, Maxwell's equations only is frightening the students, the researchers. People are afraid to come to electromagnetic theory. This is sufficient. Beta is 2 pi by lambda g. L, you can put anything from 0 to lambda g. Each length has got different. Suppose if you put 5 by 16 lambda g, you get a very important property, which is equivalent to an isotropic antenna. So that way, you take this equation, find out everything. If you want to get ZAC, put ZR is equal to 0. If you want ZOC, put ZR is equal to infinite. So that way you get JZ0 tan beta L. ZOC Z naught by J tan beta L. J in the numerator is inductor, J in the denominator is capacitor. That is what given in the Smith chart. See, nothing more than that. You got only L and C. That can be in series or parallel. What else you got? Whatever may be the current configuration, you can have a series parallel or parallel series. It's a thumb rule. Go clockwise, it's a series L. So remember this thumb rule and then keep going. This is a small example. See, the distributed theory you can express in the form of a lumped theory. And the center one is the main element. If you want to design a capacitor, think about the pi network. This is a T network center element. Is that not by J sine beta L? If you want to design an inductor, think about the pi network. How do you get this? Don't bother about all these expressions. Just think about the equivalent theorem. The easiest book I can say is John D. Ryder. The first part is the lumped one, second part is the distributed one. If the distributed theory can be expressed in the form of a lumped theory, that means one has understood both the distributed theory as well as the lumped theory. Then you can simply play like network theory. Other than LNC, what else you want to design? Because once you come to the microwaves, electromagnetic theory, when you're using silver or when you use high frequency, RNC also will not, RNG also will not come into the picture. So this is how you can design LNC. See, this is a small example. You take this is a filter, either in a microstrip line or a strip line. This will be the profile. In one case, it is epsilon effective, other case, it's the epsilon naught. Each length is lambda g by 8. If you remember lambda g by 8, what formula you need? So the people might have seen, but what I am presenting is a consolidated way. If you know everything in terms of lambda g, the 50% of the design of any component is over. This is a filter. If a person is very good in filter, he or she can do anything just like a child's play. And in the filter, every theory needed for microwaves or designing of the components will come. If you take an antenna, it is only one LC. Whereas if you go to filter, you have got so many LCs. When you are thorough with so many LC, what is the difficulty in designing a single antenna? Once you design an antenna, if that property is not sufficient, it's not meeting the requirement, then go for M by array like that. So this is one example of lambda G by 8. It's a filter. So this is the another one. You can see how the wave impedance changes with respect to lambda. People know the expression 2d squared by lambda. So that is the minimum distance you should keep whenever you want to do the antenna measurement. One more thing I would like to tell is there is one wonderful website, IEEE Microwave 101. And if you see that, it will be just like novel. It is not in divergence or curl equation. You can understand things in a very easy way. So this is how lambda plays with respect to that. So now this is the combination of so many components. Directional coupler, hybrid ring, matching elements, stub matching, filter, all you should join together. If you join, then you get the super heterodyne mixer. This is what in the low frequency you call super heterodyne mixer. The high frequency, it is a balanced mixer. If you take the center one, it is 1.5 lambda G, 3 by 2 lambda G into 2. Whereas if you take anything in the filter, each one is less than lambda G by 4. Particular one, if you want to find out, it will be lambda G by 8. So this is another example. Here, it is lambda G by 4. That only connects between two impedances. And if you take the square root of that, you get root 2 phi z net. This is another example where lambda G by 4 play a big role in the power divider. And again, this is a rat race hybrid. Upper one is 3 times of lambda G by 4, lower one is 3 times of lambda G by 4. So this is the rule. Everything is in lambda G. If you know these four, you can design substrate integrated waveguide. And the next one, two-step branch line coupler, and each series arm shunt arm is lambda G by 4. So the circumference, the perimeter is 4 times of lambda G by 4. And without knowing the sanctity of lambda G by 4, people would have designed, or people would have gone blindly, mainly the students who want to get the things in a very shortcut. This is a backward coupler, and each arm is only lambda G by 4. And again, see, if you take this structure, again you can see what is the variation in terms of the lambda G. So this is again micro electromechanical system. Again, it is lambda G by 2, lambda G by 4, 3 by lambda G, 1 by 10 lambda G. Only thing is, there it is micrometer, whereas in microwaves it is in the centimeter. You can go even to the millimeter. Whether you go millimeter, centimeter, or kilometer, it is all the jugglery of lambda G by 4. So this is our world. I told about the metamaterial, FSS, photonic band gap, whatever, all come in a planar transmission line. Strip line, microstrip, CPW, CPS, fin line, all come in the planar transmission lines. Every design, the length is very, very important. Up to the third decimal of the millimeter, it is very, very important. So these are the few things. What you see in the bottom is the waveguide version. What you see in the top, it is a MIC version. This is the summary of the formula needed for the filter. And these are all the things. You design a single antenna. If that specification is not meeting your requirement, go for M by N. Again, it is Z naught square is equal to Z into Z naught. If you go for a circumferential circular antenna to avoid the discontinuity effect, again you can tell what is the perimeter size in terms of the lambda G. So this is Yagi-Uda antenna. Yagi-Uda antenna, each director, reflector, and spacing, it is all in terms of lambda G by 4. Not only lambda G by 4, zero point 0.3 lambda G, 0.2, it has got a geometrical progression. So everything is lambda G by 4. What you can see above the building, you can keep it inside a packet. That is this one. RFID also. What I want to say is, if you know in terms of lambda G by 4, the designing is completed 50%. Power divider, power combiner, all I have shown. Everything, there are only two things you have to do. 1:4, 1:2, or two-step branch line coupler, circular way, rectangular way. Everything is some way or the integer multiple of lambda G by 4. That's all I want to tell. This is a bandpass filter. You got a low impedance, high impedance filter. Then the next one is band stop filter, end coupling, edge coupling. Once you thorough with the components, you can join together, make a system. Again, everywhere, either it will be lambda g by 4 or multiple of that. The whole total length is 2 times of lambda g by 4. So that way, if you know, see, this is my last slide. Um, the lambda g by 4, if you have, at some time, you can have the short circuit. At some time, you can have an open circuit. So this is the easiest way of having two band antenna, multi-band antenna. People say, that is one. Maybe one or two more slides I will show. This is again the same thing in a realistic way. By the jugglery of integer multiple of lambda g by 4, short circuit, open circuit can be obtained, and you can have at a time two band frequency generators. Another example of meta material. So that's also in terms of lambda. You take any of the components, it is all, it will be only in terms of integer multiple of lambda g by 4. So this is what I have experienced as take any field line, or you take your own cell phone. What about the antenna size? It is all multiple, integer multiple of lambda g by 4. So this is what I want to conclude. You take any of the components or any of the systems. It will be only in terms of integer multiple of lambda g by 4. Whether it is a MEMS, BioMEMS, RF MEMS, or MIC, or terahertz. Terahertz is the ground supported coplanar waveguide, whatever it may be. If you can realize it in the form of integer multiple of lambda g by 4, one will not forget. You can understand the subject. Designing will be in your thumb. It is not at all, it is not going to be a difficult. The other part also, you can do it very easily by knowing the impedance, characteristic impedance, and using Wheeler's curve and other nomogram, you can find out exactly up to the third decimal of millimeter or micrometer. You can design the components, the length and the width, or the whole world behind the design concepts. You take any of the substance, any of the components, you can extend this theory, and definitely maybe people would have come across like this, but this is a consolidated effort of telling that one, if you understand, if you want to know what is lambda g by 8, put in that equation and see what expression you are getting. So that way, if you understand the subject, things will become easier, and you will can be authenticating in your design work. I thank the organizer for giving me this golden opportunity. With this, I would like to close my presentation.